Hello, dear students. We are back again with another video lesson. I hope you're all doing well. I got many requests from the students to upload more videos. Inshallah, I will upload more videos in chapter 6, and inshallah, I will finish chapter 7 as well. In the previous lesson, guys, if you remember, we stopped here after we finished the RLC series connection to AC source and RLC parallel connection to AC source. We reached it here and we stopped it here, the oscillating circuit. What is the oscillating circuit? A circuit is made up of a self-inductance and capacitor connected, okay? If the capacitor is initially charged under an external source, but actually it should be a capacitor is initially charged under a DC source. Why? Because capacitor can be charged only by DC source. By what? By DC source. The capacitor is a device that consists of two parallel plates there is a separation between these two parallel plates when connected with the DC battery. The capacitor can store electrical energy. Okay, so the capacitor is a device that can be charged only by DC source, not AC source. Okay, because in AC source the magnitude and direction of the current changes continuously, so that is why the capacitor becomes charged on discharge, charge on discharge. Okay, so we cannot get the maintained charged capacitor by AC. Okay. So that is why it should be DC. It's better to write down DC here than an external source. The external source here, it means that DC source, okay? Guys, in electric oscillate or oscillating circuit, in oscillating circuit, we have inductance, capacitance, and inductance. Capacitance, inductance. LC. Okay, in electric oscillating we have capacitance and inductance. Okay, oscillating circuit. But guys, at first we have to charge the capacitor by connecting with what? With DC source. Okay, this is positive and negative. What is this? This source is DC source, like a battery. Okay. When we charge the capacitor by DC source, okay, we can see that the capacitor becomes charged, okay, and the positive charge accumulate here, and the negative charge will accumulate here, okay, because here the negative charge flow in this direction and the positive charge in this direction. Now we charged the capacitor. Now the capacitor is charged, okay? After the capacitor is charged, so we can remove the DC source, okay? After charging the capacitor, now the capacitor is charged. Now we will connect it with inductance. With what? With inductance. Okay, so in this case, Q is equal to what? Q naught. Q is when Q is equal to Q naught. What do I mean by this? It means that the capacitor is charged. Okay. Now the capacitor is charged. It stores electrical energy. When the capacitor stores electrical energy on the capacitor is charged, Q is equal to Q naught something. Okay. And I is equal to what? Is equal to 0. Okay. So when the capacitor is charged by an external source, the value of the current is 0. Yes. Okay, so when does the magnitude of the current is 0? When the capacitor charge reaches maximum. Okay, this capacitor electrical energy is stored in this capacitor. The capacitor tries to amplify this electrical energy. Okay, so by discharging the capacitor, the current flows through the inductance. Okay, so when the charge flows through the wire and it goes to the inductance, guys, look. The value of capacitance becomes 0. Now, charge is equal to what? 0. Why? Because the capacitor becomes discharged. Okay? Because when the capacitor is charged, okay, if you connect it like a resistance or a light bulb, what happened to the capacitor? What happened to the electrical energy that's stored as electric field in the capacitor? it's gonna be amplified or it's gonna be dissipated. Okay, when the charge dissipates or when the charge becomes discharged, the flow of the current passes through the inductance. Okay, now the flow of the current reaches what? Maximum. When current reaches maximum, Q is equal to what? Q is equal to 0. Okay? So when the current passes through the inductance, as in the Oersted when we studied, when the current passes through the inductance or coil, this current can produce magnetic field or induces magnetic field. Okay? Now, the current is converted into what? Into the magnetic field. So because the current changes as enters the inductance, increases and it decreases when it passes through the inductance. The magnet of the current varies. When the magnet of the current varies or changes, the magnetic field also becomes varies or changes. And magnetic flux changes. When magnetic flux changes, current is induced. According Faraday's law or Lenz's law, the induced current that induces by changing in magnetic field in the inductance is opposite to the source. Okay, so that is why this magnetic field induces the current. Okay, and this current passes through the capacitance, and the capacitance again becomes charged. Okay, guys, the induced current that induced in this inductance, it goes to what? Charging the capacitance. Okay, but be careful, the polarity of the capacitance changes. The polarity of the capacitance changes. At first we had positive here, but in this time the positive is located here. Okay, why? Because according Lenz's law, the induced current is opposite the change in the external and the source of the power, and the negative charge will accumulate here. Guys, how did we get this charge in capacitor? Also, how can we charge the capacitor in the third time? In this time, we can charge the capacitor by the induced current that induced in the inductance. Okay, and the charge again reaches maximum. Sorry. Q is equal to Q naught, but current is also 0. When charge has maximum value, current is 0. We don't have magnetic field. But when charge is 0, current is equal to what? Current is equal to maximum. Okay? So this exchanging between magnetic field and electric field, between inductance and capacitance, the energy exchange between inductance and capacitance is called what? Oscillating circuit. This is oscillating circuit. In the oscillating circuit, guys, look. In the oscillating circuit, so we have frequency. Okay, this oscillation has frequency. How? At first, the magnitude of the current is 0. Current 0. Okay, look, current. The magnitude of the current is 0 at first. When the charge of the capacitor reaches maximum, current is 0. Okay, current is 0. This is time and the current. Okay, when the capacitor becomes discharged, okay, current reaches what? Current reaches maximum in the inductance. Current reaches maximum. Okay, after that, the induced current that opposes the source of the current induces the current, and it goes to the capacitor, and the capacitor again becomes charged. When the capacitor becomes charged, current again becomes what? 0. Okay, so this oscillation will continuously, and we can find out the frequency in the oscillating circuit. The frequency in the oscillating circuit is equal to what? Is equal to 1 over 2 pi LC. What is this? This is the frequency of the oscillating circuit. This is basically about the oscillating circuit. If the initial charge on the capacitor is Q naught, then the electric energy is stored in an electric field. The capacitor discharges through the coil while the current increases to achieve its maximum value. When the capacitor loses all its charge, the energy now stored as a magnetic field. When does the energy stored as a magnetic field in the inductance? When the capacitor becomes discharged. Okay, when capacitor reaches 0. and when the capacitor loses all charges. The charge is again stored by the capacitor until the current in the coil drops to zero. The energy is again stored in the capacitor, and so on. The exchange energy repeated many times between capacitor and coil, as long as no part of it is lost through the resistance of the coil from heat. Guys, in the present, if the coil is pure, okay, this oscillating will be continuously forever when the resistance of the coil is equal to what? Zero. When the coil and when the inductance is a pure inductance, okay? If resistance of the wire is zero, if you neglected the resistance of the wire and the resistance of the circuit, this oscillation and this oscillating circuit will oscillate forever, okay, and indefinitely. Then no damping will occur when resistance is zero. Resonance circuit, the circuit will oscillate indefinitely. Any possible energy loss, when we say any possible energy loss, it means that maybe the energy loss by the friction between the flow of charge and the atoms of the wire by friction, okay, the type of the material and the resistance of the coil, it goes to losing some energy, leads to the damping. Any possible energy loss like resistance leads to what? Damping oscillation. Damping oscillations, when does the oscillating will be damping? In the presence of resistance. Look, in this case, resistance is not equal to zero. But when resistance is equal to zero, the oscillating will be continuously. If a current of a same frequency, like in this figure, current of the same frequency, and phase introduced in the circuit, resonance will take place. Resonance will occur only with the AC current, because AC current has also frequency, okay? Like for example, between capacitance and inductance, we have a frequency. Look, we have what? Frequency. The frequency of the circuit is equal to what? Is equal to 1 over 2 pi LC. Okay? If the current of the same frequency, AC source also has frequency. Okay? If these two frequencies are the same, the frequency of the circuit and the frequency of the source, if these two frequencies are matches each other, so we can say resonance takes place. Okay, the resonance takes place. What is electric oscillating? Is the process of exchanging energy. Electric oscillating is what? Process of exchanging what? Energy. Between what? Between capacitor and inductance. In the capacitor, the energy stored as electric field, but in coil or in inductance, the energy stored as a magnetic field. Okay? The energy stored as electric field in capacitor, and energy stored as a magnetic field in coil. What does the frequency of the oscillating circuit depend on? Coefficient of self-induction and the capacitor of capacitance. What causes oscillating? Damping in oscillating circuit. Damping, losing energy, okay? Due to the resistance of the coil, some of the energy loses in the form of heat. What is resonance? Guys, if you remember, we had resonance in mechanical, okay? If the frequency of two systems matches each other, as a result, the amplitude increases and it goes like to damage and destroying the bridge or the window sill or glasses or anything, okay? But the resonance, we have two types of resonance: resonance in mechanical and resonance in electromagnetic, or resonance in electricity, okay? Resonance in electricity is what? A phenomenon that occurs when alternating current, frequency of the current, with a given frequency enters the circuit that has same frequency with the circuit current. Okay? This is resonance. The definition of resonance is very important. Be careful. According to this equation, the resonance frequency depends on what? Cell of induction, L, and capacitor of capacitance. Guys, in resonance, look. In resonance, L is equal to XC. XL is equal to what? XC. XL is equal to what? 2 pi FL. How about XC? 1 over 2 pi FC. Cross product. 1 times 1, 1. 2 times 2, 4. Pi squared. F times F, F squared. L times C, LC. Okay? To find frequency, take out frequency. The variable of the frequency will go down. 4 pi squared times LC, and 1 is here. Take the square root for both sides in order to remove the square above the frequency. What does remain? Frequency is equal to 1 over the square root of 1 is 1, and the square root of 4, 2. Square root pi squared, pi. Square root LC, square root of LC. Frequency in the resonance is equal to 1 over 2 pi radical LC. What is the condition of resonance to occur? When alternating current with the given frequency have the same frequency of the circuit's current, okay, of the oscillating circuit. What does the resonance circuit is made of? Cell of indictance and variable capacitor. What do I mean by variable capacitor? So we can adjust the frequency by changing the capacitor, okay? So this is how can you produce resonance phenomenon in electric circuit. The circuit enters into a resonance when a current of a given frequency is entered to it, while the capacitance of the capacitor is adjusted to equal frequency of the current of the circuit. This is how one can tune the frequency of the radio and television station at home. When resonance takes place, the reception of the broadcasting station is possible. What is the tuning or tune? Is the act of achieving what? Resonance. What is tune? Act of achieving what? Resonance. What does the reception of the transmitting wave occurs broadcasting station? When the resonance takes place, the reception of the broadcasting station is possible. Okay? Guys, we have some important notes or tips about the resonance. Another condition of the resonance to be occur is XL is equal to XC. Okay? In series connection, guys, look. In series connection, RLC series connection. Look. RLC series connection. Z is equal to what? Is equal to R squared XL minus XC squared. Look. At resonance, XL is equal to XC. They have the same magnitude. When XL is equal to XC, the result of this bracket, it becomes 0. Z is equal to what? R squared plus 0 squared. When XL is equal to XC, XL minus XC is equal to what? 0. Like for example, 25 ohm minus 25 ohm, 0. Okay? 0 squared 0, radical 0, it cancelled. Okay? So what is remain? R squared. The square root with this power 2 cancel. What is remain? Z is equal to what? R. Z is equal to what? R. In what? In series connection. In series connection, at resonance, guys, you have to keep in your mind, at resonance, in series connection, total impedance is equal to resistance. Z is equal to what? R. Okay? And IE total is equal to what according to Ohm's law? VE total over what? Over Z. Guys, at resonance, what happened to the total impedance? If we have 0 here, if XL and XC cancel each other, what happened to the Z? Z decreases. The total impedance decreases in series connection at resonance. At resonance, what happened to the total impedance? The total impedance it decreases. Okay, why? Because XL is equal to XC and they cancel each other. So as a result, the value of total impedance decreases. When the value of total impedance decreases, guys, what happened to the current? When VE total is constant, the value of the current reaches maximum. Current becomes what? Maximum. How about Z? Minimum. So, can you write down IE total is equal to VE total over R? Yes. Why? Because Z is equal to R. Z is equal to what? Z is equal to R. When? At resonance. At resonance, the total impedance is equal to what? Resistance. Okay? The effective value of the current attained is maximum, while total impedance attained is minimum. Okay? So you can write down here IE total, VE total over Z, or VE total over R is the same thing. At resonance in RLC series connection, what happened to the Z? The value of Z decreases, but current increases. Current reaches, the effective value of the current reaches what? Maximum, while total impedance reaches minimum. Okay? But in parallel circuit, if you remember, we know that 1 over Z is equal to what? Is equal to R squared, okay? The equation, 1 over R squared plus 1 over XC minus 1 over XL squared. The situation is completely different in parallel circuit. In parallel circuit, guys, so what happened to the Z in parallel circuit? In parallel circuit, Z increases because we have 1 over Z. Okay, we have 1 over this value. When the total impedance increases, according to this equation, IE total is equal to what? VE total over Z. If VE total is constant, for example, when Z increases the total impedance, what happened to the current? The total current decreases in parallel connection. At resonance, the total effective current decreases when the total impedance increases. Okay? So, in parallel connection, the situation is completely different with the series connection. Okay? And the effective value of the current attained is minimum in parallel connection. Had minimum value when, okay? So, but it is total impedance reaches or attained is maximum. IE total in parallel connection, VE total over Z. In parallel connection, Z increases, but current decreases. Okay? So in a resonance case, the phase difference is 0. At resonant case, or at resonance circuit, phase difference is what? Phase difference is 0. Why? Because, guys, look, XL is equal to XC. So XLC is equal to what? 0. VL is equal to VC. VLC is equal to what? 0. So that is why the angle or the phase difference is 0 between the total potential difference and the total current. If you remember the phasor diagram for the, like in series connection, okay? If you remember, we have VR here, VL, VC. At resonance, VL is equal to VC. If VL is equal to VC, we don't have these two vectors and this VL and VC here anymore. So the figure will be like this, and the circuit has only resistance characteristics, okay? So only we have what? We have VR, IR. Why? Because VL and VC, they cancel each other. What is remain? Only VR, IR. Angle is equal to what? Angle is equal to 0. Angle is 0. VLC, 0. XLC, 0. V total is equal to VR, yes. Why? Because VL and VC equal. Okay? And omega L is equal to 1 over omega C. Guys, look. At resonance circuit, XL is equal to X. XL is equal to omega L. XC, 1 over omega C. Cross product. 1 times 1, 1. Omega times omega, omega squared. L times C, LC. To find omega square, it's going to be 1 over LC. Remove this power and take this radical for both sides. Omega is equal to 1 over radical LC. At resonance circuit, omega is equal to what? 1 over radical LC. The phase difference is 0 between the total potential difference and the total current. We don't have XL and XC because they cancel each other. The current of the circuit will have maximum value, which means the impedance will have minimum value when the circuit connects in series. So the resonance frequency can express in this equation. The circuit has characteristics of the pure resistance because theta is 0 and omega is equal to 1 over omega C. Omega is equal to what? 1 over radical. In resonance circuit, if the capacitor of the capacitance changes, the frequency of the circuit changes and use this relation to find this change. Guys, look. In oscillating circuit, frequency is equal to what? 1 over 2 pi LC. What is the relation between frequency and inductance? Inversely proportional. It is what? Inversely proportional. When the coefficient of self-inductance increases, what happens to the frequency? Decreases. But the relation is radical, be careful. What is the relation between frequency and the coefficient of self-inductance? Inversely proportional with the square root, with the radical. How about for the frequency? For the capacitance, the same thing. Frequency with the capacitance also inversely proportional with the radical LC, okay? So in this case, you can find out how the frequency changes, okay, when the coefficient or capacitance changes. Guys, F1 over F2 is equal to what? Radical L2 over L1. Why? Because inversely proportional. That is why we have F1, but here L2. Why? Because this relation is inversely relation. For the capacitor, this one is more practical. F1 over F2 is equal to what? Is equal to C1 or C2? C2. Why? Because capacitance with frequency inversely proportional with C1. Whenever the two capacitance are given in the question, you have to use this relation to determine how much energy, how much frequency changes by changing the capacitor. Okay? What does the impedance in a series circuit at resonance depend on? The total impedance Z depends only on resistance. In parallel circuit, resonance magnitude and the current has minimum value, but Z reaches maximum value. So we prove this equation. Okay? How energy stored in the figure shown beside? In this figure. How energy stored in this figure? Very good question. Be careful, guys. If you see the figure, capacitance, we don't have charge in the capacitor. Charge is 0. Charge is equal to what? 0. When charge 0, current reaches maximum value. When the current reaches maximum value, you know that the magnetic field stored, or the magnetic field stored in the inductance. Okay? Energy stored in the coil as a magnetic field. But when the capacitor becomes charged or reaches maximum value, current reaches 0, magnetic field reaches 0, and energy stored in a coil as an electric field. Question 41. Look at this question. If the below circuit resonates, guys, pay close attention for the resonate. Okay, whenever you see resonate, you have to pay close attention for the question. Okay, at resonate, guys, Z is equal to what? R. XL is equal to what? XC. VL is equal to what? VC. VE total is equal to what? VR. Phase difference between potential difference and current, 0. Okay, when it is feeding current, what is the effective value of the alternating current? The effective value of what? Of alternating current, IE total. IE total is equal to what? VE total over Z. The figure is given in this case. Do we have capacitance? Yes. Do we have inductance? Yes. Effective value of potential difference, VE total. Do we have VE total? Yes. Was given 220 volt. Do we have frequency? Yes. 50 hertz. Guys, how can I determine IE total, the total current or the effective value of the current? The effective value of the current at resonate, guys. Do we have Z? No. But be careful at resonate. Z is equal to what? Is equal to R. Do we have resistance? Yes, we have resistance. So can you write down here VE total over R instead of Z? Yes, of course. VE total 220. Divide by what? Divide by 22 ohm. We have resistance. Guys, don't try to find total impedance. We don't need total impedance in this question. Okay? Sometimes the student, they try to find out the total impedance. And okay? So at resonance, you are not necessary to find the total impedance. Because at resonance, the total impedance is equal to R. Do we have R? Yes. You can replace and you can find the total effective current. Okay? Question 42, one of the very good question, be careful. Resonant circuit is made up of inductive coil and variable capacitor. What do you mean by variable capacitor? It means that the capacitor can change its value. We can adjust the capacitor. If the capacitance of the capacitor is lowered from lowered. What do you mean by lowered? It means that capacitance get decreased. When capacitance decreased, frequency must be what? Increases. Why? Because relation between capacitance and frequency inversely proportional with the radical. Okay, inversely proportional. The capacitance, the capacitor is lowered from what? C1, 400 times 10 power negative 6 farad. You have to convert microfarad to farad multiplied by 10 power negative 6 to what? C2, 100 times 10 power negative 6 farad. If you see, you can see that the magnitude of the capacitor decreased from 400 to 100. When capacitor decreases, frequency must be increased because its relation is inversely. So what happens to the frequency of the circuit? F2 is equal to how many times F1? We have to find this relation. Guys, look, how can you determine this relation? At first, you have to write down the relation between frequency and capacitance at resonance. At resonance, F2 over F1 is equal to radical C2 over C1. F2 over F1, C2, 100. 100 times 10 power negative 6 divided by 400 times 10 power negative 6. Okay? F2 over F1 is equal to what? Negative 6 with negative 6 cancel. This to 0 cancel. What does remain? 1 over 4. Guys, look. Now, F2 over F1 is equal to radical 1, radical 4, 2. Okay? F1 is equal to what? Yeah, it's gonna be 2. F2 over F1, yes. 2 F1 is equal to what? 2F2 is equal to what? F1. Okay? So F2 is equal to what? Guys, look. The frequency must be increases in the second time. Look. Or there is something wrong here. C here is, no, it should be F1, sorry, C1. Guys, look. F2 over F1 is equal to C1 over C2. C1 is equal to what? Sorry, guys, I made some mistake here. I do apologize. Once again, listen carefully. F2 over F1, C1 over C2, because it is inversely related, okay? F2 over F1 is going to be C1 400 times 10 power negative 6 divided by 100 times 10 power negative 6. F2 over F1, negative 6 cancelled. 2 zeros with these zeros cancel. What does remain? 4 over 1 is equal to 4. So F2 over F1, radical 4, 2, radical 1, 1. Cross product. 1 times F2, F2. 2 times F1, 2F1. The second frequency, the frequency in the second time after lower capacitance, it becomes twice as much of the frequency in the first time. So F2 is gonna be what? Twice as much as F1. One of the very good question. Be careful. Look at this challenging question. It's a very good question. Okay. If the coil's resistance and pure resistance are given in the question, you should find the total resistance, guys. If you remember in RLC series connection, we studied that the total impedance in RLC series connection is equal to what? R squared plus XL minus XC squared. What is this R? This is the pure resistance or the resistance of the coil? This is both. Okay? So can we say that this is our total use? In the equation of total impedance, what do you mean by this resistance? This is only the resistance of the pure resistor? No. This is only the resistance of the coil? No. This is total resistance. Total resistance is equal to what? Is equal to R of the coil plus R of the pure resistor. Okay? We studied this in RLC series connection. Now I'm going to explain again. Listen carefully, please. Look, guys, if you have a circuit made up of like inductance, look, we have AC source, inductance, capacitance, resistance. Okay, but the coil has resistance. The coil is not pure. Okay, the coil is not pure. If the coil is not pure, what do I mean by not pure coil? It means that the coil has resistance and XL. As we studied, inductance with the AC source, if the coil is not pure, has both resistance and XL. Okay. Here we have R of coil, and as well we have XL. And we have C, XC, and resistance of what? Pure resistance. What is this? This is the resistance of the pure resistor, like a light bulb, okay, or anything, any device. What is this? This is the resistance of pure resistor. But this is the resistance of the coil. Because in this coil, to find V coil, how can we determine V coil? If the coil is pure, V coil is equal to VL, IXL. But if the coil is not pure, V coil is equal to what? Is equal to V across the resistance of the coil square plus VL square. Okay? And to find Z in this case, we have to add up these two resistance here. Okay? This is the total of these two resistance. Look at question 52. In question 52, we have two branches, branch A and branch B. Branch A, it doesn't relate with the resonance. Okay, only branch B related with the resonance. Be careful. In branch A, we have RLC series connection. Okay, without resonance. An RLC series circuit is made up of a coil of cell of inductance L. We have L, 15 millihenry convert to Henry multiplied 10 power negative 3. And resistance. Resistance of what? Of the coil. The question does not mention the coil is pure, or doesn't mention the coil negligible of resistance. The coil has both inductance, inductive impedance XL and resistance. What is this resistance? This 10 ohm. This is the resistance of the coil. Is equal to how many ohm? 10 ohm. A capacitor of capacitance 200 microfarad. This is C. This is L. And resistor of resistance. What is this? This is the resistor of the resistance of pure resistance is equal to what? 12 ohm. If you draw the circuit in this question, we have AC source, a coil of resistance, and we have a capacitance, and we have resistance, okay, connected with the AC source. Guys, the coil is not pure. Coil is not pure. When the coil is not pure, it means that has containing resistance. The coil has resistance. When the coil has resistance connected with AC source, has both XL and resistance. Okay? And also the magnet of this resistance is equal to what? 10 ohm. Is equal to what? 10 ohm. And the resistor of the pure resistance was given 12 ohm. The total resistance is equal to what? Total resistance is equal to 10 plus 12, 22 ohm. Okay? And what is unknown? If the effective value of the source, V effective, is given 100 volt and frequency 60 hertz, find the effective value of potential difference. What is unknown? Effective value of potential difference across each of the coil. V coil, V capacitor, V resistor. What is unknown? V coil, look, V coil, V capacitance, VC, V pure resistance, VR. How many unknowns do we have in branch A? 3 unknowns. V across coil. When we say V across coil, so we have to count only for the coil or resistance, for both. Not only for the inductance. V coil, VC, VR. How can we determine V coil? V coil, because the coil is not pure, is equal to VR squared, VL squared. Do we have VR? No. VR is equal to what? Is equal to I times R of the coil. VL is equal to what? VL is equal to I times XL. VC is equal to what? VC is equal to I XC. VR is equal to I R of the pure. This R is 12 ohm, but this R is 10 ohm. Okay? Guys, how can you determine V coil? At first, V coil is equal to VR of the coil, VL squared. VR, we don't have VR. VR coil is equal to IR times R. But we don't have current. In this question, we don't have current. How can we determine current? Current is equal to VE total over Z. VE total over what? Z. Do we have VE total? Yes. 100 volt. Do we have total impedance? No, we don't have. We don't have total impedance, guys. How can we determine total impedance? The total impedance is equal to R total plus XL minus XC squared. Do we have R total? No, but we can find R total is equal to R of the coil plus R of the pure, which is equal to 22 ohm. XL we didn't have, but we found by using 2 pi FL, XC 1 over 2 pi FC. It's very easy. You can replace in order to find what? Z. Now, do we have Z? Yes. The circuit is series connection? Yes. Series connection. In series connection, the amount of the currents are equal? Yes. IE total is equal to what? 100 divided by 23.3, which is equal to what? 4.3 ampere. What is this 4.3 ampere? This is I total? Yes. IR? Yes. IL, IC? Yes. Why? Because it is series circuit. Replace into this equation to find VR of the coil, VL. After that, replace into this equation to find potential difference across the coil. After that, potential difference across the capacitance and potential difference across the pure resistance. For the pure resistance, you have to use 12 ohm. Okay? Guys, branch B, the frequency of the alternating current. What is the known frequency of the alternating current? Allows the circuit to what? Resonate. At this frequency, the circuit does not reach the resonance. We have to find at which frequency the circuit reaches the resonance, or at which frequency allow the circuit to resonate. Frequency is equal to 1 over 2 pi LC. Do we have L? Yes. C. Just at 92 hertz, the circuit becomes resonant. Okay. That's all for today, guys. Inshallah, in the next lesson, we will finish all questions that related with the resonance, and inshallah, we will study the transformer and transfer efficiency in chapter 6. Inshallah, after finishing chapter 6, inshallah, I will promise you that I will upload the video for the chapter 7 as well. Thank you for listening. Keep up your best day. Have a good time.